Welcome to our Quantum Deep Dive.
Hello.
Today, we're really plunging into the work of Charles Henry Bennett. I mean, a true titan, wouldn't you say? His ideas basically shaped quantum information theory.
Absolutely. A real pioneer. And for this journey, we're drawing on some really insightful work by Jurgo Schnepphat. Key excerpts, really, that detail Bennett's life and, well, his profound contributions.
Right. So our mission here, our goal for this deep dive, is to really get to grips with his big ideas.
Yeah, things like, quantum teleportation, quantum cryptography, and understand that connection he saw, that fundamental link between information and the physical world.
It's about grasping why his work is so important, right?
Yeah.
Foundational, really, for this quantum age we're sort of stepping into.
Why it matters now.
Okay, let's unpack this a bit. Bennett's path wasn't exactly straightforward into quantum physics, which I find pretty fascinating. Born in 1943, started in chemistry, actually. Bachelor's of Brandeis, then a Harvard PhD under David Turnbull. So, how does someone starting there end up revolutionizing physics and computer science?
Well, it's a great question. And it really highlights his unique perspective, how he crossed disciplines. His interests just evolved, driven a lot by the sheer power of computers back then.
The 60s, 70s.
Yeah, that whole era, that technology kind of pushed him away from pure chemistry towards thinking really deeply about information itself, information theory.
And here's where it gets really interesting for me. The key insight seems to be grasping that information isn't just abstract. It has a physical reality.
Yes.
And wasn't that heavily influenced by Rolf Landauer?
Oh, absolutely. Landauer, another brilliant mind. They were colleagues at IBM where Bennett ended up.
Right.
Landauer had this groundbreaking principle. He basically showed that deleting information, erasing it irreversibly, isn't free. It's a physical act. It has to generate heat. Yeah, linking information loss directly to entropy increase. Bennett took that idea and just ran with it.
So landing that job at the IBM Thomas J. Watson Research Center, that seems like it was way more than just a job for him.
Oh, it was crucial. Definitely. That environment, it offered this unique mix of disciplines. Physics, computing, information theory, and the resources, of course. Perfect for someone like Bennett who was bridging these gaps.
So his background, moving from chemistry, thinking about information.
Yeah.
It gave him a fresh lens.
Exactly. A new way to look at problems. And that's what led him ultimately into the quantum world.
Okay, so to really understand what Bennett did there, we probably need to touch on a couple of core quantum ideas, just briefly. The ones that were kind of the building blocks for him.
Fair.
First up, qubits and superposition.
Right. So, classical computers use bits. Always 0 or 1. Simple. Qubits. They're different. Because of superposition, a qubit can be, sort of both 0 and 1 at the same time, to different degrees.
Which lets quantum computers do things differently.
Yeah, potentially perform many calculations in parallel, store vastly more information. This non-binary nature, this quantum weirdness, was definitely key to what pulled Bennett in.
And then there's the other big one, entanglement. This always sounds like, pure science fiction.
It really does. It's that mind-bending thing where 2 or more qubits get linked. Their fates become connected instantly, no matter how far apart they are.
Measure one and you immediately know something about the other.
Exactly. That's what Einstein famously called. Well, he was worried about it. Spooky action at a distance.
Right. Spooky.
But for Bennett, it wasn't just spooky or curious. It was like the key ingredient, the essential piece for his biggest breakthroughs, especially teleportation and cryptography.
So, okay, he has these quantum concepts. How did he build something revolutionary? Let's start with that link back to thermodynamics, Landauer's principle again.
Right. So he dug deeper into this idea of reversible computation. If deleting info costs energy, generates heat, could you compute without that cost?
Could it be done without irreversible steps?
That was the question. Bennett explored how, in principle, computation could be reversible. You could theoretically undo every single step. This connects computation and thermodynamics at a really fundamental level.
Suggesting maybe quantum computing could be more energy efficient?
Potentially, yeah.
Yeah.
By avoiding those irreversible information losses. It's a deep idea.
And this leads us to maybe his most famous idea, or at least the one that sounds most futuristic, quantum teleportation. Now, it's easy to get this wrong. We're not talking Star Trek beaming.
No, definitely not beaming Captain Kirk anywhere. The breakthrough, which he worked out with collaborators like Richard Josa and others, it was showing you could transfer the quantum state of a qubit.
The information.
Exactly. The information, the essence of the qubit from one place to another without the physical qubit itself ever making the journey.
Okay, so how does that work? The source kind of breaks it down into steps, doesn't it?
It does, pretty clearly, actually. Yeah. First, you need an entangled pair of qubits. You create them, link them up.
And give one to the sender, Alice, say, and one to the receiver, Bob.
Right. Standard setup. Second, Alice, the sender, performs a special kind of measurement. She measures the qubit whose state she wants to teleport along with her half of the entangled pair.
Okay, she measures them together.
Yep. And crucially, the result of that measurement, just classical information like zeros and ones, gets sent over a normal channel.
Like, yeah, an email, a phone call, whatever. Not quantum.
Exactly. That's the classical communication part.
Yeah.
Then Bob, the receiver, takes that classical information.
The measurement result.
And uses it, along with the entangled qubit he already has, to perform a specific quantum operation on his qubit.
A little tweak based on the message.
A precise tweak. And if he does it right, poof, his qubit is now in the exact same quantum state as the original one Alice had. He's reconstructed the state.
It's astonishing that it works using entanglement and classical info together like that.
It really is a beautiful piece of theoretical physics.
And then there's the other huge contribution. The one that maybe had the most immediate real-world impact or potential impact, quantum cryptography.
Right, specifically the BB84 protocol, developed with Gilles Brassard.
BB84. Bennett and Brassard, 1984.
That's the one. This was truly pioneering stuff. They figured out how to use quantum mechanics itself, its inherent properties, to solve a massive problem in security.
Which problem?
How to securely share a secret key, the key you need for encryption. How do Alice and Bob get the same secret key without an eavesdropper, Eve being able to steal it without them knowing?
And the quantum property they used. It was the measurement thing again. The act of looking changes things.
Yes, that's the absolute genius of it. The fact that measuring a quantum system inevitably disturbs its state. That's not a bug, it's the security feature.
How does it work in BB84, roughly?
Okay, so Alice sends Bob a stream of qubits, photons usually. She prepares each one in a random quantum state, chosen from different sets of bases. Think like polarized light, vertical, horizontal, or diagonal, random choices.
Okay, random bases.
Bob, on the other end, measures each incoming qubit. But here's the trick. He also chooses his measurement basis randomly for each qubit. He doesn't know which basis Alice used.
So sometimes they'll match, sometimes they won't.
Exactly. And after all the qubits are sent and measured, they talk publicly. Over an open channel, totally insecure, anyone can listen.
But what do they say? Not the results, surely.
No, never the results. They only compare the bases they used for each qubit measurement.
Ah, so they say for qubit number 1, I used the diagonal basis, me too, or nope, I used horizontal.
Precisely. Huh. And they keep only the results where their bases matched. They discard all the others.
And the results from the matching bases, those should be identical if everything went right.
Identical. And that sequence of identical results becomes their shared secret key.
But where's the security? How does Eve get caught?
Because if Eve tries to intercept and measure a qubit mid-flight, she also doesn't know which basis Alice used.
So she has to guess a basis to measure in.
Right. And half the time, statistically, she'll guess the wrong basis. Her measurement will collapse the qubit's state, altering it.
And when Alice and Bob later compare a sample of their key results from the matching bases, they'll find discrepancies, errors.
Exactly. Those errors reveal Eve's presence. The act of eavesdropping leaves an undeniable physical trace in the quantum states. It alerts Alice and Bob that the channel's compromised, and they just scrap that key and start over. Security guaranteed by physics.
Wow. That's incredibly clever.
Yeah.
The source also mentions, briefly, his work in algorithmic information theory.
Yeah, it touches on that. Connecting the complexity of something to the length of the shortest possible computer program or algorithm that can describe or generate it. Ideas like logical depth.
How much computation it takes to produce something.
Kind of, yeah. It really shows the breadth of his thinking, linking computation complexity even to understanding quantum systems.
And it really hammers home how vital those collaborations were, doesn't it? Landauer, Brassard, Joseph.
Oh, absolutely fundamental. His work thrived in that collaborative space, building on insights from different fields. It wasn't done in isolation.
So let's shift to the impact now, today. Where are these ideas actually playing out? Quantum teleportation. It's not just theory anymore, is it?
No, far from it. It's become a really foundational tool in the whole vision for quantum networking.
The quantum internet.
Exactly. The idea of linking quantum devices, Sending quantum information securely over long distances, teleportation is key for that.
And for things like linking quantum computers together. Distributed quantum computing.
Yes, and also for developing things called quantum repeaters. You need those to overcome signal loss when sending quantum states over long optical fibers, for instance. Teleportation is part of how repeaters work.
Okay, and BB-84. That led directly to QKD, quantum key distribution.
Right. QKD is the practical application of those BB-84 principles. It offers this entirely new way to handle secure communication. Security based on physics, not just mathematical difficulty like current encryption.
Because eavesdropping is detectable immediately.
And QKD is definitely moving out of the lab. You see governments using it, financial institutions exploring it.
Early networks are being deployed too, right? I think the source mentioned China, Europe.
Yeah, there are active deployments and serious investments happening. It's becoming a real-world technology, albeit still niche.
But beyond just the specific tech, Bennett's work kind of forged a whole new field, didn't it? Quantum information theory itself.
It really did. It brought physicists, computer scientists, mathematicians together in a completely new way. It created this vibrant interdisciplinary research area, shaped university courses. It's huge.
So his theories aren't just history. They're the bedrock for a lot of current R&D.
Absolutely. In quantum computing, things like developing new algorithms, running simulations, in quantum communication, his ideas are constantly being built upon, refined, setting the stage for future breakthroughs.
Okay, but it's not all smooth sailing. The potential is massive, but actually building this stuff, there are big challenges.
Oh, definitely. Huge challenges. Decoherence is probably the biggest one.
Qubits losing their quantum magic.
Basically, yeah. Quantum states are incredibly fragile. Any interaction with the environment, heat, vibration, stray fields, can make them collapse back into classical states, losing the quantum advantage. You need extreme isolation and control.
And incredible precision.
Exactly. And even with QKD, which sounds perfectly secure in theory, real-world implementations aren't always perfect.
You mentioned vulnerabilities.
Yeah, things called side channel attacks. These don't break the fundamental quantum protocol, BB-84 or whatever. Instead, they exploit flaws in the physical devices used.
Like how much power the laser draws, or the exact timing of signals.
Precisely. Tiny physical imperfections that might leak information about the key, even if the quantum part is sound. It requires really careful engineering to plug those holes.
So it raises technical limits, obviously. Building stable, large-scale quantum computers is still incredibly hard.
Very hard. We're talking maybe dozens or hundreds of reliable qubits now, not the millions you'd need for some applications.
And it also brings up bigger societal ethical questions, doesn't it?
For sure.
The big one is quantum computers potentially breaking current encryption. That's a massive threat to, well, everything digital.
It's a huge motivator for developing QKD and post-quantum cryptography, absolutely. Then you have worries about surveillance potential with advanced quantum sensors.
And the risk of a quantum divide if only some nations or companies have this powerful tech.
Right. Unequal access could definitely create new power imbalances globally. These are really complex issues we're only just beginning to think through properly.
But the cool thing is, Bennett's work doesn't just pose problems. It also inspires solutions.
How so?
Well, things like quantum error correction. You need that to build reliable quantum computers that can fight decoherence. And the ideas behind error correction, they draw inspiration from principles like reversible computation that Bennett explored.
Ah, interesting connection. And researchers are constantly working on improving teleportation, making QKD more robust, developing new quantum algorithms.
All building on that theoretical framework he helped establish.
Exactly. His foundational ideas are still actively guiding the research, trying to actually harness the quantum world.
So his legacy seems pretty clear and enduring. It's not just theoretical. It's driving real scientific and technological efforts today.
Totally. To sort of wrap it up, Charles Henry Bennett's pioneering work, quantum teleportation, BB-84, quantum cryptography, reversible computing, it didn't just contribute to quantum information theory. It fundamentally shaped it. It laid the essential groundwork.
Yeah, he really was a visionary, seeing that deep, deep connection between information, physics, computation at the most fundamental level, and bridging fields that didn't used to talk much.
His vision just keeps inspiring people, pointing towards this future with potentially revolutionary quantum networks, much more powerful computers, and security based on physics itself.
And we've been able to take this deep dive thanks to those insights from Jorgo Schneppet's essay excerpts. So maybe a final thought for you, the listener, as you reflect on this quantum future, sparked by Bennett's incredible ideas. Think about the profound societal shifts it might bring, both the amazing possibilities and those complex ethical questions we touched on, questions we'll all need to grapple with.
Goodbye for now.